Good morning, everyone. So I'll let people trickle in and grab their seats, and want to welcome everyone to another annual research day for the Toronto General Hospital Research Institute. I'm going to do my usual year in review, but before I do that, I'd like to welcome and invite our Executive Vice President of Research, and that's Dr. Bradley Waters. Brad.
Thanks, Mansour, and it gives me a great pleasure to welcome everyone here again this year to the TGHRI Annual Research Day. These days are great opportunities for the Institute and its members, its scientists and clinicians to come together for a couple of reasons. And one of those is to look back and to take stock in the accomplishments and some of the science that has gone on over the past year. And to look at that performance in aggregate in some ways, and to look at it in context. And it also gives you an opportunity to spend a day together to interact. And it's really this opportunity which is unique across institutes like the Toronto General Hospital Research Institute, which contains a diversity of different strengths in different diseases, in different research areas, in different disciplines. And it's this opportunity that provides you with an exploitable advantage over your colleagues and over your other institutes. And it's something that we need to really consider and to work on to take advantage of as we go forward. As you know, the UHN has gone through a process of renewal over the last 2 years. And this began with the establishment of what is known as UHN's PVP, its purpose, values, and principles. That was officially launched last year around this time in November. And the purpose statement, as you will have seen from UHN, is stated as transforming lives and communities through excellence in care, discovery, and learning. And this is extremely important from the context of UHN as a research hospital. It's stated in our purpose that UHN exists to transform lives in part through discovery and through learning. It's part of the makeup of UHN. It's what makes us different from other hospitals across Toronto and Ontario and Canada. UHN is committed to discovery, to research, and to advancing care for the future. And this purpose statement really set the foundation for the development of UHN's new strategic plan. And that strategic planning process began in January of this year and has taken place throughout the year to set a course for the vision and for the mission of UHN going forward. And much of that work had neared completion and was due to be presented to the board in September of this year. And as you know, our CEO, Peter Pisters, has been poached. He's leaving UHN to return to Houston, where he spent 20 years as part of his career, to take over the CEO and president of the MD Anderson Cancer Center, which is the largest cancer center in the world. And while it's disappointing to lose Peter, especially halfway through a major renewal and the development of a strategic plan, I think it's also an indication of the position and the influence that UHN has on the world, that the largest cancer center in the world picks the CEO out of Toronto to come back to Houston. But there was a lot of work done in that strategic plan, and we're writing up the work that was done, and it was really around, in terms of vision, it was around 3 general themes. And one of these was around population health and the move towards a population health-based healthcare system. This is something that's mandated in legislation, the Patients First legislation, and it's meant to move us away from a transactional, episodic-based healthcare system to one that takes care of the health of the population throughout the healthcare continuum. And we see examples of where the research that's going on in this institute is already within this realm. The research in liver and hepatitis, in diabetes, which is extending out into primary care, trying to identify patients early through screening processes. evaluation of minimal residual disease, advanced diagnostic procedures to understand which patients need which kinds of therapy. And this sort of approach, as we develop more effective therapies and more effective medicines for our patients, is going to be an increasing part of improving healthcare for the future. The second major theme was around digital and the move to a digitally enabled healthcare system and a learning healthcare organization, the ability to capture vast amounts of complex data with every patient that comes to the hospital, data associated with their clinical care, data associated with diagnostic tests, genomic tests, imaging tests, and other kinds of data that we gather with our patients, with a move towards using real-world evidence to make treatment decisions. And of course, we see examples of this that are very active in this research institute as well. The area around cardiac care, the development of tools to be able to monitor patients and capture data, and to use that data for making informed treatment decisions before patients arrive at the hospital. And the final theme was one which I think is particularly important for this community. And it was that third theme was around building strength through greater alignment of our clinical and basic research objectives, and greater alignment of our across UHN and across our institutes. And this is really the strength that we have at UHN. UHN last year spent almost $400 million on its research effort. This makes UHN the largest research hospital in Canada by almost a factor of 2, one of the largest research hospitals in the world, and represents 20% of our entire budget at UHN committed to research. Just to put that in context, that level of funding is equivalent to the 9th or 10th largest commitment to research across any organization, across any company in Canada, similar to what IBM or Rogers spends on research, which are $13 or $14 billion companies. So a commitment of 20% of our activity in research or to research represents an unusual and an unbelievable commitment to the research enterprise. And the advantage that we need to think about, and which I challenge all of you to do, is to think about how to align and to synergize and to go deep on that kind of investment. This means alignment of our basic priorities around fundamental and discovery research with the biggest clinical opportunities in the clinic. Alignment around cardiac disease, around diabetes, around transplant, around regenerative medicine, around immunology. And there's incredible opportunity here. We're in a very fortunate situation in terms of the level of commitment that our foundations make to fund research. The Toronto General Hospital Research Foundation last year raised almost $100 million directed towards research. And this kind of support is what makes UHN and that makes this kind of commitment to research possible. But there's opportunity for better alignment in all of these areas, aligning those investments with the biggest priorities. And that's going to be part of that vision going forward. We're going to be launching our research strategic plan in the next month or so. This is going to begin with a lot of stakeholder involvement and a lot of input from all of you. And it's going to build around these concepts that were laid out in this first part of the UHN strategic planning process. So the search for our new CEO is underway. A search firm has been established and a search committee is established. There's a website on UHN you can go to see who's part of that and to see how that is updated. There's a commitment on the board to do this quickly, to have a new CEO in place by February next year. And we look forward to moving forward on that strategic planning process at UHN and to dovetail that into what we're going to be doing with research. So I want you to enjoy the day. I'm looking forward to hearing from all of you and from Mansour and in terms of the year in review. And I hope you have a great time. Thank you.
Thank you, Brad. So over the next 15 minutes or so, I'm going to try and just give you a high-level overview, as I've done in previous years, of sort of where we are, state of the union, if you will. So here's the bullet points of what I hope to take you through. We've been growing. I'll give you an update of where we are with our publication metrics, our budget and financing, and some important recognitions of our faculty, how we're doing with tech transfer, and to emphasize, I think, our need to continue to engage our trainees. And finally, I'll share with you where we are, as Brad has, in terms of our strategic planning that was conducted last year, and how it might map to where UHN is in its overall plan. So I want to first begin by reminding everyone of our structure and my gratitude to the group leads and the division leads. In advanced diagnostics, it's Myron Cybulski. In support systems and outcomes, it's Murray Cron. In cardiovascular, it's Slava Eppelman, who's a new group lead. In metabolism, it's Mina Wu, a new group lead. In infection and immunity, it's Adam Gehring, a new group lead. And not to change everyone all at once, in respiratory and critical care, it's Ming Yao Liu. And in communities of health, it's Shabir Alibai, who've been the two stable group leads for the duration of my tenure as director, which is now in my 6th year. We are now 143 individuals with formal appointments at the Toronto General Hospital Research Institute. As the pie chart will show you, 72% of those are clinicians, and 28%, which is actually a growing number over my 6 years, are non-clinician, essentially PhD investigators. And we break out as follows. There are 99 people with formal primary scientist appointments and 44 with affiliate scientist appointments. The affiliates are either clinicians with a heavy research footprint or actually faculty from other institutions who require access to and collaborate in a meaningful way with UHN-based investigators. There are an additional 131 Toronto General Hospital-based clinical researchers who do not have a formal appointment with the Research Institute, but whose grants still go through. If there are issues of access of equipment or access of facilities, we still kind of administer much of that, although to some extent that's also taken care of by their clinical departments. So the profile, of course, is you'll see over the years that the numbers have slowly been growing. This is growth despite some level of attrition with retirements and whatnot. But it's nice to see, even in the current CIHR funding environment, that we've been managing to grow. And I think a lot of credit does go to our foundation that's been supporting this. So how do we seek appointment? I remind people of this every year. We're looking for people with strong publication records, strong research potential and proposals. We really look at their communication skills, their potential for leadership in the field. And as Brad has mentioned, I think alignment becomes ever more important. It's always a challenge for me when a great potential scientist who may not be directly aligned with the clinical programs at the hospital is in our community or wants to join our community. That can become a real challenge because our funding so much depends on the alignment with the clinical programs. We do both strategic and opportunistic recruitment in both clinical and basic realms. All recruits that are supported by the Research Institute must go through a search committee, which I'm or my delegate are a part of, and we get other relevant stakeholders. They are open international searches. Even if it is the recruitment of an internal candidate, we will debate at length whether we need to do an international search for the opportunity just to see who else we may be able to attract. And sometimes the benefits of that is we end up hiring 2 people instead of the 1 person that we wanted to just get. Here are some of the new faculty that I want to welcome. Carolina Alba is a scientist in the cardiovascular group in support systems and outcomes. Bettina Hansen is in support systems and outcomes in infection and immunity. Andrei Krushinsky is an assistant scientist in infection and immunity. And Beata Sander is a scientist in communities of health support systems and outcome. And there are new affiliate scientists who are appointed here. Nicholas Mitsakis, Jacob Pendergrast, and Karen Okranik. So again, you'll notice that a lot of these are all in support systems and outcome, which is an area that we believe is very well aligned with the strategic growth areas of TG, and we hope to continue to recruit in that area. I want to congratulate those people who were scientists and promoted to senior scientists. They're shown here: Ian McGilvray, George Tomlinson, Bruce Perkins, and Keyvan Karkoudi. This is a significant achievement. It's the equivalent of a 10-year review at any university, and all of these individuals passed with flying colors. My congratulations go out to them. We are a productive group. This is a 5-year rolling metric that I've shown you every year to show you the top line there of the 95 faculty that were here for those 5-year rolling average. We have almost 3,000 papers. It's about 6 papers per investigator per year, with a mean journal impact of just under 6. Almost 12% of those papers in impact factor journals greater than 10. And with a subject area median impact factor of 3.2. That means that in that subject area, our scientists are publishing on average with an impact factor 3-fold above the median for the field, and about 15 citations for every paper. Every division has something to be proud of. Support systems and outcomes per investigator basis, almost 9 papers per investigator per year. The advanced diagnostic has the highest impact factor as a division, and the highest number of papers that achieve impact factor greater than 10 are from experimental therapeutics. So everyone's contributing to this laudable productivity. The trend in terms of our publication and citation metrics are shown here. So it's a healthy increase in papers per investigators per year. It was about 5.3 5 years ago, and it's now over 6. And on a large institution, that's a meaningful difference. In terms of impact factor, we've been steady, right about journal impact factor 6. And in terms of a number of papers that are published in journals above impact factor 10, it's actually been a slight decline. We were sort of 12 to almost 13, and now we're just under 12. So I want to encourage people to always aim high. A few examples. I could have picked many, but lovely paper by Phyllis in PNAS about the role of P53, the RB protein, pocket protein in cardiac tissue hemostasis. So borrowing from cancer, where this has been well studied, into cardiac. David TGHRI is probably the best known nephrologist studying how certain drugs that act on diabetes affect the kidney in both type 1 and type 2 diabetes. I myself go to a fair number of cardiovascular diabetes meetings, and not a single meeting that I go to doesn't mention David's productivity. And I often see David more at those meetings than I do in Toronto. Ian McGilvray, a beautiful paper in Nature Materials about how nanomaterials are cleared by the liver. And Kevin Kane, how the loss of this vascular protein, angiopoietin-1, is associated with more severe and fatal malaria. And importantly, if you administer angiopoietin-1, you can actually, in mice with cerebral malaria, you can improve survival. So important paper in Science Translational Medicine. And Charmaine Locke, with an entirely new approach to dialysis catheters. This is an endovascular AV fistula with fewer complications, minimally invasive as opposed to the traditional method. So transforming care and her analysis of that. And finally, again, demonstrating the breadth of what we do. This is the risk of fractures in individuals who suffered stroke, paper in neurology by Moira Capral from Support Systems and Outcomes. And as I mentioned, I really literally could have spent the entire hour highlighting some of the high-impact papers from our group. We do this all on a pretty modest budget. It's $6.5 million. 53% of that is spent on compensation for our salaries. And when you add in some stipends, modest stipends that we're able to give for people who function on committees and other leadership roles, comes to just under 60% of our entire budget. Our total salary costs, when you add in our extremely important administrative staff who look after our scientists, is just under 80%. So it leaves about 20% for everything else. And really of that, only half is what you might call discretionary, but it's usually our contributions to recruitments, and therefore there's actually very little discretionary budget. And yet we manage, I think, to support a very large research operation. Brad mentioned that it's $400 million UHN-wide. Well, $90 million of that comes from Toronto General-based researchers. You'll appreciate that That's a $12 million increase year over year. And some other important metrics. We know CIHR funding is tough. Our CIHR funding is actually up to $10 million over $9.8 million, but it still represents only 11% of total research spend at TG. And our foundation provides 35% of the total research spend. That's $32 million, and it's up, $6 million from last year, which is great because I think it actually contributes half of that year-over-year increase. Here's just a quick metric of how it's been increasing, and shown better here by division. You'll see the green bars are CIHR, pretty flat. And so we've seen healthy increases, sort of more stable, slight decline in support systems and outcomes, which I hope that recruitment trend there is going to help reverse. The overall success rate at the last CIHR competition was 12.6% in the foundation scheme. UHN success rate was remarkable, it was 24%. At TG, we had several people get to the final phase, but my congratulations go out to Myron as the only individual in the last cycle who was funded out of TG for his work studying the progression of atherosclerosis. In terms of the project scheme, the national average was just under 21%, and TG was right on that. The UHN success was, again, better than ours. It was 25%. We got about half of our $10 million budget through that last competition. And my congratulations go out to all of these individuals who were successful in the CIHR competition. So some other areas where we've been blessed is Heart and Stroke Foundation. This represents only 2% of our overall budget. Nonetheless, important awards, grant and aid awards, Moira Capral with a mid-career award, and Andre with an Emerging Research Leader Initiative award. We've had a couple of SPORs. The big SPORs were last year, but Shabir was successful in getting a Catalyst grant for innovative clinical trials. Phyllis Bilia renewed her clinician scientist, and Brian Coburn and Adam Gehring and Jordan Feld both got CFI GELF awards. So my congratulations to them. And to CRC renewals. Dr. Mina Wu and Marcelo Sapel both renewed their Tier 2 CRCs. And it's always great when one of our scientists gets probably the highest accolade the public can give, which is the Order of Canada. Sharon Walmsley, for her pioneering work in HIV, senior scientist in our institute, received this recognition this year. Some words about invention and disclosure and technology transfer. So the graph is a little bit small, but the blue bars represent the external funding. The orange bars represents the disclosures. And it's the gray bar that actually represents disclosures per $100 million of funding. So this is an area where I think all of UHN, but in particular TG, we believe that we can do better. I'll mention in the agenda that there's some opportunities for any of you who want to talk to our technology officers in the agenda. They're here today and are looking forward to discussing things with you. There have been some notable successes. So Blue Rock Therapeutics is a new startup funded by Bayer and Versant, really focusing on regenerative medicine. The cardiac headquarters is based in Toronto, work with Gordon Keller and Michael Laflamme. This is a really exciting initiative for the entire stem cell community, but particularly in terms of translating clinical cardiac regenerative medicine to clinic. NeuroShield, senior scientist Joe Fisher has, with Dr. David Smith, invented this device that is designed to protect against concussion or brain injury. This has been licensed to a company that's really a spin-off of many TG inventions. This is a nice success story. And there are many others. Again, I could have shown them. So I want to, again, put a shout out to our postdoctoral seminar series. This is held on a regular basis, often twice a month. And it's a full schedule. I invite as many PIs as possible to attend. It's well attended by the trainees, I know, and we welcome ongoing participation. I want to congratulate the trainees who've gotten a number of external recognitions, the Banting Award, the Crescent CIHR Award, CIHR Fellowships, and a Health Systems Impact Fellowship, and all those trainees that are listed here, my congratulations to you. I also want to make people aware, working in the cardiovascular realm, that the Rogers Center is now a really good source of postdoctoral funding. and there are 4 individuals here who received support from the Rogers Center. And this is generally comparatively undersubscribed, so look into that as a source of funding. Let me end with just a few words about strategic planning. So last year, we enunciated together as a community this mission: scientific excellence and discoveries leading to the best in patient care in a collaborative and supportive environment. And Brad has already mentioned UHN's purpose. I think there's some themes, particularly the discovery and learning, that we align with very well. We talked about sustained leadership in life-changing discoveries in care. I think it aligns very well, life-changing, with the needs of our patients coming first, which is UHN's primary purpose. And if you look at the UHN values of safety, compassion, teamwork, integrity, stewardship, at least 3 of those map directly to our collaboration, communication, person-centeredness. And of course, as a research institute, we want to have curiosity and excellence as part of our values. So I believe we're actually in good shape to participate in the remaining strategic planning that Brad discussed, and I would welcome all of you to remain engaged, either electronically or in person, at the town halls, at meetings. It's important that your voices be heard. This is also sort of bittersweet. Tracy has left after 5 years, really, with almost my entire tenure. She's moved on to join Diabetes Action Canada as a manager of research operations. She's been in that position for several weeks and yet has sort of single-handedly put together today's day. So my many, many thanks to Tracy and congratulations to her. I also want to welcome Kathy Chow, who's our new business administrator. She's literally started a few days ago. She will be at the normal directorate offices. Her contact information is there. I'm terribly excited to be working with Kathy. I've heard nothing but blazingly bright recommendations. She's worked at Peter Munk, at the arthritis, and at the Can Help C program. So she's very experienced at UHN, so I want to thank her for joining us and welcoming her. And we are still recruiting a business manager role for the Institute, which I hope to share with you shortly. So here's our agenda. It's a packed agenda. I'm going to now remind everyone that we have 2 poster sessions. These are moderated poster sessions. All of the other posters will be available in the poster rooms, but there's going to be 1 set before lunch and then another set after lunch. I want to thank the leadership team for helping me evaluate all the posters. There were so many, and the space being limited, that for the 2nd year now, we've had to limit the number of trainees able to present their posters. 6 have been judged to be sort of special, if you will. They're all excellent. This is very difficult judging, and they're going to be presented by the people in front of a judging panel, and we're going to announce a winner at the end of the day. The afternoon is listed here, and again, I'm to remind you that our technology development and commercialization officers are available to answer any questions during one of the poster sessions in the poster room. So enjoy the day, and with that, I'm going to welcome Myron Cybulski to introduce our first keynote speaker, Professor Diamandis. Myron.
Today to introduce Dr. Eleftherios Diamandis, my colleague and division head of clinical biochemistry at Mount Sinai Hospital and biochemist and in chief at University Health Network. Eleftherios has a long-standing and distinguished career focusing his research activities around the discovery and validation of cancer biomarkers, proteomics, mass spectrometry, and translational research. He has published over 600 research papers, 133 reviews, a number of books and book chapters. His work is highly cited with over 50,000 lifetime citations and an H-index of 111. He has received a number of awards for his research endeavors, including mentoring of trainees, and he has supervised over 20 master's students and over 30 PhD trainees during his career. So without further ado, I'd like to invite Dr. Diamandis to present a very interesting story today on Theranos scientific irreproducibility, and other matters, lessons and solutions. Welcome.
So good morning, everyone. The only problem, I don't see any slides here. Okay, I see the slides now. I first like to thank Mansour for the kind invitation to present to you. I see a lot of young people in the audience, which I think it suits my presentation. Now, let me just make a disclaimer here for you, that this is not going to be a hardcore scientific lecture. It will be superficial with very simple concepts, okay? My work on mentorship, challenging others, scientific publishing, impact, represents side projects for me. And as Myron said, our lab is primarily interested in calligrines, proteomics, biomarkers, male fertility, and neurodegeneration. And I'm sure many of you will say, why on earth you came here to waste our time on side projects? But actually, it wasn't my fault. I say, if you want to complain, it's all Mansour. When he invited me, he said, speak about your side projects. Okay, so if you don't like it, complain to him, not to me. That's what I was told to do. So let us just get down to this issue of reproducibility. What is scientific irreproducibility? If you ask an elementary school student, will tell you that these published papers are not reproducible by independent investigators. And a lot of people believe that these papers that are not reproducible are published in cheap journals. But in actual terms, most of the, and I will come back to that later, most of the most dangerous irreproducible papers are published in the big journals, the Natures and the Sciences and the Cells and so on. Now, lately, if you open any issue of Nature or Science, they will talk about the reproducibility. Nature actually went a step farther, and I'm not sure if you are aware of it. They appointed a reproducibility editor, Monia Baker. So a lot of people wonder, is that a new problem? And the answer is absolutely not. If for some reason, recently there is increased awareness of irreproducibility, and a lot of people are talking about it. Now, I'm not a newcomer in the irreproducibility business. In actual fact, in 2006, I published this paper in Clinical Biochemistry, it's a small Canadian journal, in which I say that was written specifically for the young people. And it was an advice to the young people, and I say, as I cut and paste from there, we need to alert the younger scientists that the scientific literature is full of incorrect and or irreproducible data. This is also known as crap. And train them to exercise caution when they read the literature. The word crap was not in the original paper, okay? And at the same time, my compatriot, John Diamandis, who many of you probably feared of, he published a provocative paper in PLOS Medicine in which he said why most of the research findings are false, outlining again that they are not reproducible. Is the reproducibility costly? Well, there was a recent paper in PLOS Biology which says 28 billion are wasted to irreproducible papers. And if you look at these graphs here, when Amgen tried to reproduce 50 papers for their own use, they found out that 90% of them were not reproducible. Same with Bayer. 90% not reproducible. And others found at least 50%. So if one calculates the cost of this, to society comes down to about $28 billion, represent irreproducible science, and $28 billion represent reproducible science. And I will outline later what are the reasons for irreproducibility. The $28 billion reminded me of another story I wrote in clinical chemistry in 2015 with Mr. Bean, Dr. Bean, as I called him. And I said the NIH is wasting $20 billion. But that was for a different reason, but the amount was about the same. And I calculated how much time we spend in writing grants that are not funded. Dr. Mansoon mentioned 10%, 12%, 15%. I said 15% success rate, and I calculated how much time we spend for the 85% of time that our grants are not funded, and I found out that we are wasting about $20 billion. It's actually alarming because, as we all know, and it's a fact, most of our grant obligations end up in the garbage bin, not being funded. By the way, I'm very good in identifying solutions, but I'm not good in finding solutions. Identifying problems, but I'm not good at finding solutions. So part of my scientific life has been a policeman. My wife said, you could have been a very good policeman here instead of a scientist. And the reason is that over the years, with a self-initiative, I took on a lot of people and I challenged them on papers that appear to be not necessarily fraudulent, but incorrect. And I cite here a number of papers that I challenged over the years, big papers like in Lancet, Journal of Clinical Investigation, and some of them even in Nature and so on, in which I challenged the authors for their findings. And in most cases, I actually won the argument. If you look at the history of it, I won the argument. So with this in mind, I decided to, I like this taking on people. So I decided to take on more people and see what happens. And one of the people I took on, as Dr. Mansoor wanted today, was this young scientist called Elizabeth Holmes, who started a famous company called Theranos. If we have time at the end, I will get back to Theranos and tell you a few more specific things. But in actual terms, this $9 billion company in 2015, I challenged them with actually a series of papers. There were 6 papers that were published over the 2-year period, criticizing the Theranos technology, the Theranos approach, and I predicted that they're not going to succeed in anything. And the truth of the matter is that the company is now in huge trouble because whatever they promised didn't really pan out. For those who are interested on the details, the papers are there. You can read them. If you go to PubMed and search Diamandis and Theranos, they will all come back. Theranos was not the only people I challenged. I challenged the big Leroy Hood. I'm not sure how many of you know about, but this is a big scientist out of the Institute for Systems Biology in Seattle. And I challenged him on a concept that he called 4P medicine, which is kind of a personalized medicine for the masses. And he claims that the more you test on these people, the more the health benefits for them. And I counter-argued that the more you test people, the more likely that over-diagnosis and over-treatment will occur. We published our debate in a journal, BMC Medicine, a couple of years ago. Since that time, Leroy Hood created a company, because that was the whole idea behind it, to commercialize this, called Arrivail. And in the August 2017 issue of Nature Biotechnology, they present the so-called pilot data on 108 individuals who went through their intensified monitoring and testing for the purpose of improving their health. I am writing a counterpoint on this already because I invite you to read it. I think it's just kind of crazy that this guy is measuring 2,000, 3,000 analyzing the blood of these people. He's doing whole genome sequencing, whole microbiome, And he claims that with this kind of approach, he will identify occult diseases, which eventually he will treat and everybody will be happy. But as we all know, it's not that simple because of 1,000 reasons, false positives, false negatives, and so on. And then my appetite has increased, and I said, let's just take on some more people. And more recently, we co-authored a paper on the circulating tumor DNA, which, as you may know, is the hottest field in cancer biomarker diagnosis, monitoring, predicting therapeutic response. And of course, we are not claiming that circulating tumor DNA is no good. We claim that circulating tumor DNA may not be good for early diagnostics for small tumors, and we have something that we have submitted already and is under review. I remind you here that the big people that you see in this slide are the big Gates and the Bezos and the Amazons and the Googles of the world. They actually formed a company called Grail, in which they put in $1 billion of money, $1 billion, and they say Grail will save the world by doing early cancer diagnostics, and then we can excise the tumor and everybody will be happy. But I don't think this technology will actually work based on theoretical grounds that we analyze in our papers. And we have future plans. My future plan is to challenge Donald Trump and Kim Jong-un. Some notes regarding irreproducibility. The failure to reproduce a paper does not mean that the findings of that paper are wrong. And the opposite is also true, that if you reproduce a paper, it doesn't mean that what you reproduce is either important or right. We have to be careful on this. So, in order to tackle irreproducibility in science, there was a irreproducibility or reproducibility consortium formed, which they say we're going to reproduce 50 papers, big papers, and see how many of those are reproducible. But we all thought immediately that this was a crazy idea because trying to reproduce a paper is not trivial, it may be highly costly. It will be highly slow. So we had questions, and very quickly this reproducibility consortium, they said, oh no, we cannot do 50 now, it's just too big. Let's just do 5 and see what happens. And when they did the 5, with a lot of time and effort, the results were actually equivocal. They could not say if they reproduced the paper in its full content or they didn't. So this kind of tackling reproducibility is not very good, so I came up with a very simple, almost like a trivial idea, which I will present to you later, of how we believe we could tackle reproducibility. And we have 2 papers now in press describing our own little approach to it, and I will come back to it in a minute. Now you will all ask, what are the reasons for this irreproducibility? What are the reasons? Well, there's not one reason. We identified about 6 or 7 reasons. One of them is fraud. People publish fraudulent papers, as we all know. They fabricate the data, but this one is a very small percentage of the whole irreproducibility problem. But I will give you an example. And then there is this other category which involves big investigators, Nobel Prize winners, who are becoming so overconfident that they publish crap. I will give you examples. And then there is the issue of bias, which is mostly related to study design. And the bias is a major threat to irreproducibility because if you have a bias in the design, you will get biased results, which means not reproducible or not generalizable. Technical deficiencies is a big problem. Fragmented science is a big problem. And bioinformatic glitches are a big problem. And I will give you an example of this very quickly, of each one of these. How many of you believe that a fraudulent paper with totally fabricated data can pass the rigorous scientific review of nature or science? It could pass. Many of you believe that it could pass. Could it pass twice or 3 times in nature? It's actually, I believe, I never tried, by the way, but I think it's going to be almost impossible to draft a paper that is totally fabricated and pass nature stringent review, maybe once, but not twice or 3 times. Now look at this guy. I call him a malignant genius because this guy published all these papers in Science and Nature and other big journals, and then he retracted. Now listen, he retracted 7 papers in Nature. They were totally fabricated. He retracted 9 papers in Science, which were totally fabricated, and other big papers. So if I were to be on the Nobel Committee, I will give this guy a special Nobel for being able to trick 7 times 3 or 4 Nature reviewers and 9 times 3 or 4 Science reviewers. It's just amazing, but it happened. Amazing. Now, in terms of overconfident investigators publishing crap, a few years ago, I described a disease which I call Nobelitis. If you go to PubMed and search the word Nobelitis, there is one paper will come out, this my paper in 2013. And I say, what is Nobelitis? Well, it's a disease that is afflicting Nobel laureates. And it goes like that. The most common symptom is megalomania, in the sense that the gold medal from Stockholm is a passport for saving the world, whatever this means. And then the Nobel seems to provide reassurance that the laureates have some superhuman powers that they did not realize before, and that the prize will give them a chance to go on and do even bigger things. It's almost like these Nobel laureates, they say, you know what? I didn't know I was that good. I can do anything now with my medal. And this is when they start writing crap. Now, after publishing this paper, I discovered that there is a very similar syndrome that was described by Owen and Davidson. Owen was the Minister of External Affairs of the United Kingdom in some period, and he noticed that politicians, once they exercise power, they have personality changes. And he called that hubris syndrome, from the Greek word hubris, and I will tell you what it is. So in Greek mythology, the offenders will be expected to get punishment from the gods, something that is called panacea. And what is hubris? Is the arrogant pride of those humans who call themselves as being equal to God. I'm asking you before I show the slide, do you know of any people who have documented and for sure hubris syndrome? Can you name one person that you know and say, this one has hubris syndrome? No? I'll show some. But before, this is a classic example of hubris. It's the story of Daedalus and Icarus. You know, Daedalus did the labyrinth in Crete, and he wanted to escape with his son, and King Minos would not allow him, so he created these wings with wax, and he flew with his son. And he was telling the son, don't go close to the sun because the wax will melt and you will go. And Icarus exercised hubris. He would not listen. He went up, and then the wax melted and he went down the water. That was the panacea. That was the punishment from the gods. But here are some people that you know very well, which Owen said they have documented hubris syndrome. How would you not say this guy had hubris syndrome? Trump. Anyway, when you see him, look at the description of hubris and you say that's for sure. Now, there are also regular guys who can suffer from hubris syndrome. We should be aware of this. Now, some of the most brilliant people in the world had documented hubris syndrome, including Einstein, Charles Darwin, and Linus Pauling, who published crap because they were so overconfident. The most classical example is Linus Pauling, who had 2 Nobel Prizes and 2 blunders due to hubris. One of them, as you know, he proposed the triple helix structure of DNA, which was totally, completely wrong. And the other one was his notion that vitamin D can cure cancer. And the historians who studied his behavior said that both blunders that he had was due to hubris. He was overconfident because he scored wins over other groups, and he became so confident that he thought he was infallible. Very dangerous to feel that you are infallible. So I created this slide a lot many years ago to tell the young people that stay with what you do best and don't try. You know, many of like Bunting, the guy who, our own Nobelist from Toronto, who discovered insulin. I'm not sure if you know it, but as soon as he discovered insulin, he said, now that I cured diabetes, I'm going to try and cure cancer. And he did some very bad work with cancer because he didn't know anything. So this slide tells you, stay with what you do best. If you're good in basketball, play basketball, not baseball. So the learning point for the younger people is that in science, hubris may lead to fraud or to unfounded publications. And I tell the younger people, I hope they listen to me. Learn to exercise humility, not hubris. Now, the bias as a reason for irreproducibility is well known to you. Bias means that people can use inappropriate controls, wrong statistics, or interpretations, or variance in the procedure used. An example is the study of heart disease that uses only males, and we all know that this one, the findings cannot be extrapolated to the entire population that includes women and other ethnic groups. Now you may say, yeah, bias is obvious, we can see the bias, but actually not. Some forms of bias are very obvious. For example, somebody is doing prostate cancer research and his control group are 25-year-old men, which they never have prostate cancer. That's an obvious bias. But in most cases, the bias can be so subtle that you cannot recognize it even after years of looking. And I have some examples. I authored this paper in the Journal of the National Cancer Institute in 2010, in which I give 7-8 examples of bias that could have not been ever imagined. Very difficult to find in some cases. And yet we have fragmented science. What is that? Well, when I was young, 100 years ago, I used to publish a paper with 2 authors, 3 authors, 4 authors. Now you go to Nature, you open, the author list is longer than the papers they publish. And what does this mean? It means that pieces of the work is done in various places, and justifiably. But the problem is that somebody has to write the paper as a coherent piece, and how would everyone know what the other people did in their lab with the piece that they did? Is it good or bad or indifferent? And this kind of so-called science being done in pieces is very dangerous if you don't know what the others have done. And a classical example of this is a paper, 2 papers that they were published in Nature in 2014. I'm sure many of you remember this Obokata scandal, in which he said, I have a new way of reprogramming stem cells, very simple. And the co-authors of this paper was the famous, maybe the most famous Japanese scientist, Teruhiko Wakayama. He is a big author. He is still publishing every issue of Nature. You find a paper of him. So this guy was on the paper because he did one piece. But most of the work was done by Obokata in Sasai's lab. And then when people tried it and it didn't work, the paper was retracted, and Wakayama said something I believe stupid. He says, why don't you just get the paper back and see what is reproducible and republish it? Why didn't he check the first place anyway? But the tragic story, this tragic story is that Sasai, the middle guy, he actually committed suicide after the papers were retracted. So there are consequences with this kind of fragmented science. A classic example of bioinformatic glitches is the case of Jeffrey Chang. This guy published stellar papers in Science on crystallography, but then people, when looking at his structures, they found out that his structures were not very sound, so they went back and they questioned him. And he retracted all the papers because he wrote a little script in the bioinformatics part. He wrote a little script which had a mistake. It was reversing the plus sign to a minus sign. And all the structures went wrong, and the guy got major awards. He was nominated for this and that, and then they found out that all was wrong. So when you do your bioinformatic analysis, be very careful, if you can, to check if what you put in the computer and you press the button, what comes out actually has any relevance or it may be totally irrelevant data. In our latest editorial on irreproducibility, we classified irreproducibility into benign and malignant, like cancer. So what are benign papers or benign irreproducibility? Well, benign irreproducibility are low-impact papers written by low-impact authors, okay? They have no consequence on the progress of science. So you know why? Because nobody reads the papers. Who would ever care? So if they are reproducible or not, it doesn't really matter. And then there is so-called pre-malignant papers, in which we say these are medium impact papers written by medium impact authors. They make some noise somewhere, but they will not likely lead to new drugs or to therapies or to awards or high citation numbers. So we call them pre-malignant. But here's the big problem with irreproducibility, is actually with the malignant papers. And what is a malignant paper? It's a paper in a high-impact paper published in a high-impact journal like Nature. And the consequence, where they describe a novel therapy or treatment, and they make it as a major advance in science, but at the end of the day may not actually represent the truth. If you want to identify a malignant paper, go to the last sentence of the discussion. And invariably, you're going to find exactly this document in the end. The last sentence says, our results, if replicated, may lead to new therapies with high societal impact. Okay. Now, curing malignancy, as you know, is very difficult. Why? Well, because if you were to challenge, you have to fight the big authors, sometimes Nobel Prize winners. You have to fight big journals and big institutions. And the people like me and you, if you're going to stick your neck out, you have to be careful because you may risk your reputation if you lose the challenge. You may even risk your career, or if you go after a product, you may actually get sued. And more importantly, irreproducibility may have metastasized to more irreproducible papers, so you have to fight them more and more to get the truth out of it. So I caution you, if you are going to challenge people, you have to be very careful not to kill yourself, because if you're not sure, you may end up with big troubles. It happened to me once. I will give you a personal story here. I still have 15? So 15 years ago, I challenged a big author for a big Lancet paper, and the paper was about a new diagnostic for ovarian cancer. They said, we found it, it's 100% sensitive, it's 100% specific. When I look into it, I said, there's something wrong with here. So I challenged them, I wrote a letter to Lancet, and then we ended up with points, counterpoints, and this and that. And it so happened that at the same time I was interviewed by a Nobel laureate who was president of a prestigious cancer institution. I won't say what, but I'm sure you know which institution it is. And the guy said, you challenged this big guy about this and that. And I said, yeah. And he said, and I said, I think I'm right. I think his interpretations are totally wrong. And he said, listen, I don't know the facts, but I know only he's big and you're not as big. So I have to make a judgment. I go with the big guy. In the final end, I won the debate, but I lost the job. Okay, so what's our leader's suggestion about this? It's a simple suggestion, but I suggest that you think about it and give me input if it makes any sense or not. We say, for one thing, it's impossible to go and reproduce all these papers that are out. It's just not possible. It's costly, difficult, and it may not even be technically feasible. So we say the authors of papers with big translational or commercial importance should be obliged to write a 5-year reflection. And they tell the audience what happened to the paper. Any errors identified? Are claims still valid? Is there led to any commercial product or licensing or a startup or anything? And they say the reflection should become part of the PDF. So somebody says, this is what they said 5 years ago. Let's see what happened to this paper, because no paper is tracked. You see, you listen to CNN today that somebody discovered the cure for cancer or anything, and then after a year, everybody forgets about it. And if you ask, where is this paper? I have no idea, everybody forgot. But they shouldn't be forgotten. They should be asked, hey, what happened here? So I tested this about 10 years ago when I thought of it, and I said, let me ask these big authors to write the reflection. And I invited 20 of them, and you know the result. None of them accepted to write the reflection. They said, what, are you crazy? I'm not writing anything, for the obvious reasons. But I now suggest that the journal should say, if you publish a paper, you have the obligation to write the reflections if you are asked to know what happened. Now, let me ask you a question and see how the audience will respond. Let's say that there's a new paper describing a novel method to screen for ovarian cancer with a sensitivity of 99% and a specificity of 99.8%. And then somebody reproduces this, and he said, I reproduce everything you did. I found 99% sensitivity, matched exactly, but the specificity is 98%. How many of you believe that this is a good reproducible result? There is one who says it's reproducible. It's close enough, but in actual term, if you put it into the clinical scenario, this is actually useless. I'll tell you why. If you screen 100,000 people for ovarian cancer with a prevalence of 1 in 4,000, you can pick up 24 out of 25 positives that exist in that population, but with 99.8% specificity, you're going to get 200 false positives, and your predictive value will be 10%, which is okay. But if your specificity drops to 98%, then you're going to get 2,000 patients with false positive results, and your positive predictive value is going to be 1%, which is useless. So you see here that the boundaries of a paper being reproducible or not reproducible is actually very difficult to judge sometimes. So what are the benefits of what we suggested, the reflection? Because people say, oh, they're going to tell us what happened. But actually not, because we believe that if somebody knows that they will write a reflection in 5 years, we believe they're going to be a lot more careful in the conception of the idea, in the planning of the idea, in the execution of the idea, and the publishing of the idea. So it could actually influence a lot more steps than you think. And this one originates from a philosophical position of somebody called Tetlock and Lerner, two people. And I want to ask you how many agree with this statement. If you are asked to make a prediction, these people suggest that if you are going to be held accountable for your prediction is always more accurate. Does it make sense? If nobody cares about your prediction, you can say anything you want. You can say in 100 days the world will be destroyed. But if somebody says, well, I will check in 100 days, and if it's not destroyed, then I will say that you're a liar, then your prediction will be a lot more conservative. This is what this theory says. And we agree to it that if somebody is going to knows that they will write a reflection in 5 years, they will be very careful in the conceiving the idea, the planning of the experiments, the execution of the experiments, and the publication. And I'm not going to read all this, but I'm just saying that if you're not going to be held accountable, you can make any predictions you want and you can take shortcuts. But if you are going to be accountable, you may be a lot more conservative. Now, the public literature has caught up with irreproducibility, and there is a book, a popular book that just came out in 2017, in which now they alert the taxpayers, and they say this book, Rigor Mortis, they say how sloppy science creates worthless cures, crushes hope, and wastes billions. So now the public is going to become more aware of this. Do I have another 5 minutes for Theranos? So Mansour asked me to tell you about Theranos. It's a very interesting story because of the various parameters that they came into Theranos. First, Theranos was created, believe it or not, by a 19-year-old dropout, for university dropout, Elizabeth Holmes. Well, it's amazing to believe that a 19-year-old can actually create such a company, because the company received a $9 billion valuation in 2013-14, I think. Elizabeth was voted the best 30 under 30 in North America, and she was the youngest billionaire ever. So it is an astounding success. And here is the big promise she made, and I'm not sure if you share her vision, but she said, we're going to test asymptomatic individuals, which is equivalent to population screening. And she said, with inexpensive and easy access to the information running through your veins, that is, you do your blood test, people will have an unprecedented window of their own health. A new generation of diagnostic tests could allow them to head off serious afflictions from cancer to diabetes to heart disease. That's a very simple approach. He says, I test you, I find what's wrong with you with a symptomatic situation, and I cure you, and everybody's happy. It's actually very similar to what Leroy Hood is preaching. So they developed a little machine which we are going to do multi-analyte testing, bargain, cheap prices, quick results, avoid venipuncture by doing finger pricks, and then they put all these little machines in places like pharmacies for people to go and test themselves. And you can see on the side their blood collection device with finger prick. And this is a picture of the Theranos being at Walgreens pharmacy. The patient can go there, get the results directly. They can do self-testing and self-interpretation. When I wrote the very first paper on Theranos, I identified some weaknesses, which I summarized for you here. I think that it's still questionable if patients can actually do self-interpretation. Patients can compare 89 to 90, but if somebody, and if 90 is normal and 91 is abnormal, they won't be able to understand the difference between 89, 90, and 91. They just don't know. They believe that there is a difference. And I give examples in my writings of why this is the case. The screening issue is not a clear-cut health benefit. Believe it or not, you know it, even for major diseases like breast cancer and prostate cancer, we still don't know after 30 or 40 years of research if screening is actually beneficial or harmful. Not because screening is not identifying what we want, but it's identifying a lot more than we want, and we go to so-called overdiagnosis and overtreatment. I'm sure you're familiar with it. So the benefits of screening are not clear-cut. During this exercise, we know, as clinicians and scientists, that there will be a lot of false positives and a lot of false negatives, but the lay people will not understand that, and there will be consequences of false positives and false negatives. Fingerprinting is relatively easy to do, but it's not the ideal specimen for testing because sometimes it contaminates with the interstitial fluid, and you may get very erroneous results, especially for electrolytes like potassium and so on. And there have been examples of people complaining that their potassium with the Theranos was in the lethal range. Now, Theranos did a lot more mistakes in their testing facility. They had problems with quality assurance, and they concealed them. They were not transparent with their problems in-house. They had a very weak advisory board. The advisory board, some people said, is stellar, but it was 3 generals and 3 politicians instead of being medical scientists. So they didn't know anything about the testing. They also misled the public on the assay procedure used. They thought they had their own leader machine that was doing it, but in actual terms, without anybody knowing, they were using machines that we use at Toronto General and other hospitals to do the testing. And they were cheating on people, saying that we do it on our magic machines, but they were actually using regular machines. And then they exercised secrecy. They had no publications, no external evaluations, and they protected their technology so well inside that nobody knew what the technology was actually. So looking after it, after 2-3 years, now the company is is not worth anything. It went from 9 billion to 0. They said, what lessons did we learn from this exercise? Well, the importance of transparency through external evaluations and publications. If you're not transparent, you will pay the price somewhere. The health technologies they use, this is the lesson that I want you to remember. If you have a weak technology, no matter how much money you put in advertising, no matter how many people to pay, you will not succeed. The results will be weak, and the technology will be destroyed no matter what you do with marketing. If you mislead the public, this will come back and haunt you. If you have good data, let the data do the talking, not the lawyers. And be proactive. Hire knowledgeable advisors from the beginning, not when you have trouble. So I will close here by thanking the young summer students who helped me put together this presentation. I will be happy to discuss with you. If you have any questions, I'll be happy to answer them. I'm sure you want to ask them.
But I actually think it's one of the most important lectures delivered at any Toronto General Hospital Research Institute Day, so I want to thank you. I want to thank you very much. Eleftherios, can you tell us, is it because of the nature of your work running a clinical biochemistry department that you became aware of this because new technologies were emerging, new papers were being written? Is it your unique circumstance that led you into these side projects? Give us some context of how this has almost become, a flag that we planted.
It gives me an opportunity to give some advice to the younger people. I believe my side projects have flourished. Many of my side projects flourish, and a lot of people know me from my side projects, because I tried during my whole career to have a more spherical view of what's going on in science. One of the most difficult problems I have with my own graduate students is to get them to read widely. And they don't do it because they say, I just don't have time. I want to excel in my leader project, but I don't know anything else. Once you have a more global view, you start to understand what's going on in science, not only scientific advancements in other fields, but also what's going on with publication practices, impact factors, whatever you mention it, irreproducibility and the like. So to answer your question, I think let's just make it a relative success of my side projects is because I meticulously read every week Nature and Science magazine, especially the starting pages, not necessarily the papers, but they have inserts, they have special reports, they have reports from other journals. And Anna Konvalinka is a great friend and collaborator. She knows that in my own journal clubs, I present to my students all kinds of weird things. And they believe are weird, but I believe are relevant because it helps the students expand their sphere of knowledge. And if any of you want to excel in this kind of approach, you have to be aware of what's going on in various fields, and this can be done only by reading. If I were to select one journal, I would say, I'm not advertising, I will read Nature, especially the early pages rather than the late pages, and see what's going on in other fields. And then your mind starts to say, well, maybe I can do something on my own here. So I hope the young people will take the message, but how many will do it, I'm not sure.
Hi, thanks. It's David Urbach, Support Systems and Outcomes. That was an amazing lecture, and I think the Theranos story is a really interesting story because it seemed like everyone was just going along with what, in retrospect, was a highly implausible scenario. And I think without your papers and your criticism, it may have carried on for several more years and become a big industry in just doing blood tests and screening and providing information to patients with all their electrolytes and other blood tests that may have, as you say, offered little value and potentially health harms. I'm wondering what led you in the first place to suspect that there was a fraud in the company? Was it the fact that she was advocating just direct patient access to their own laboratory blood tests, or was it something about the technology that they developed with these nanotubes and being able to do regularly analyzed blood tests on finger stick samples as opposed to phlebotomy samples?
It's a very interesting question. Let me just answer the question in two parts. First part, one of my earliest challenges of people who publish, like the Lancet paper in 2002, somebody, a big authority, published a paper and he says, we got this ovarian cancer diagnostics with 100% sensitivity and specificity, which it's impossible to achieve because of the nature of the patients and so on. So one of the funders of our research called me on that day and he said, you know, Diamandis, stop developing any more ovarian cancer biomarkers. And I said, why? He said, because somebody published the ultimate method. It's 100% sensitive and specific, and you cannot beat that. And I was kind of rather annoyed because I said, let me just look at this paper inside out and see what it is. And in reading the paper more and more and more, I realized that what they were trying to claim, they simply cannot be true. So I wrote the first letter to Lancet, which was published, and he said, I don't believe in this paper because of X, Y, Z. So that was my motivation, that they were threatening what we were doing with something that it likely was not correct. Now, let me tell you about the Theranos. You're going to laugh to it, but it actually relates to Peter Pisters, Brad. Peter Pisters. When he took over, our director of the LMP at UHN, he said, Diamandis, we are thinking of closing the labs for a new technology. And I said, what's the new technology? He said, listen, there's a company called Theranos that is so good that we're going to close the lab and we're going to bring in Theranos. They will do all the testing. It's going to be fast. It's going to be cheap. It's going to be everything, and you cannot beat it. So we're going to bring in Theranos. So I went back and I said, let me see what this Theranos is. So I went in and I tried to dig out information. Then I said, you know what? This is all baloney. So I started formulating, and I wrote the first paper, and I had big difficulty in actually publishing because nobody wanted to publish it. But this is for the young people again. One of your elements of success with this kind of exercises is to try and learn and find out, become a friend with an editor, even of a small journal that is indexed. So I have such editors, friends, who when I send them, they're usually very positive. They say, okay, you said you will publish it. So he published, most of my critique was published in small journals because they could not be published in peer-reviewed, big type of journals. Nature would never take this kind of thing. So it was because of this stimulation by Peter Pisters coming and saying, I want to change things to the magic Theranos solution. The problem is to go and have a look. And then I found out that it was not as good as I thought. After our papers, the Wall Street Journal, as you probably know from the story, they took the message that there was something wrong, and there was a reporter called John Carreyrou. He went in and he found people, interviewed people, and he found out what's the dirty laundry of Theranos, and he exposed them in Wall Street Journal, and then boom.
One of the solutions that you proposed was that authors write a 5-year perspective after publishing a high-impact paper. Have you approached some of the larger journals? Are they interested in this, considering the fact that you mentioned that Nature now has a reproducibility editor?
We are in the process of actually trying to get journals to ask authors, but it's very difficult. I don't think Nature will take it. I know the reproducibility editor, and we talk about it, but they don't want to take the task and do the actual survey because it's not to their best interest to do it, I believe, but eventually they may be going to have to do it. Somebody has to do it, and I think it's a good proposal that they should be implemented. But how would you enforce it? I'm not sure.
The thing that you didn't mention in your talk was the issue of these new journals that are popping up that the lay press has recently picked up on, predatory journals, I think that they call them. I guess under your classification, they would be in the benign category?
No, benign journals are actually, I consider them legitimate journals, but they're small impact. The predatory journals is a different thing, which is a malicious way of making money out of unsuspecting authors. That's a different category. We wrote a paper recently on the changing landscape of scientific publishing. And I invite the younger people to read it because there are so many new models of publishing now that are coming out that may be of interest to younger people who want to publish. Most importantly, I was highly impressed with a new journal. I have no stake at it or whatsoever, but I just like their approach. It's called F1000 research. Anybody has read this, knows what this is? It's a new way of publishing with light review, but I think the most important thing is that the reviews are published alongside the paper. They are open reviews, and they are even citable. You can cite the reviewer. And the journal is giving you the option to accept the reviewer's comments or not bother with it. But if you don't bother with it, the catch is that somebody may say the reviewer told them to do so when they didn't do it because the review is citable. And I think it's a revolutionary new way of totally transparent review, and I like it very much, and I think this journal will go up in the future. It's a new approach. Brad?
So that's great. I'm glad that Peter Pistris has helped your career.
Right.
The question I wanted to ask, you talked about the various sources of irreproducibility. One of the things you didn't have on there was our structure and the role of the universities, the research institutes, people like Mansour, in ensuring the creation of a system which rewards science that is reproducible and scientists that produce reproducible kinds of research in terms of promotion systems, recruitment policies, advancement committees, and so on. I'm just wondering what your thoughts are on this aspect.
I'll be honest with you, and I may sound like a cheap guy, I am against putting barriers to publishing. For example, somebody may say, why don't you just screen all the papers that come out of UHN or the University of Toronto, and if they seem to be low quality or whatever, suspicious, we won't let the authors do it unless they go back and redesign the paper. I'm against this totally. I think people should have the right to publish whatever they want with light review, but with the catch that I introduced is that they should be held accountable for what they publish. And I think that would be a better system because I don't want to silence somebody who has a crazy idea or whatever idea they have. Let them publish it, but they should be held accountable. So if the idea is no good, they'll pay the price because they say this guy published this, but it's a piece of crap. So between the systems of a lot of regulation versus no regulation, I'm favoring the no regulation, but with the people who publish being accountable for what they say. I may be wrong, but that's my opinion.
Well, thank you very much. I think the time has come for us to have the coffee break. We're a little bit late, so instead of 20 minutes, it'll be a 15-minute coffee break. So I would ask everybody to be back in your seats and we'll start at 11:15. Thanks very much.